All right, everyone. So let me continue the last part with multicollinearity. I was supposed to record this last night, but I didn't have the time. So let me finish with this third video. So we were talking yesterday about what we did in class on last Tuesday, and I was talking about the case in which we have x2 and x1 are perfectly collinear, and we said that this would be the equation that would connect them, right, in which x2i is equal to a lambda and a lambda x1i. So as you can see, in this example, we're putting under the assumption that lambda could be any number that is not equal to 0. So, or you can call it non-zero constant. So if you can think of lambda of any number, so I gave you an example, just an easy example. I said, what if lambda is equal to 1? So 1 is a non-zero constant. So everywhere you see lambda, you just replace it with 1. But as I had here, like you can just think of any other number. You can make lambda equal to 3, you can make lambda equal to 0.5, you can make lambda equal to 2, any number. So any number that is not equal to 0, we will end up with this situation in which the numerator is equal to 0, the denominator is equal to 0, the parts of the numerator cancel out and the parts of the denominator cancel out together. So that would make for us the estimation of the parameters undefined, so you will not be able to estimate it, and this is something that we said in class. Okay, and this is all under the important assumption that x2i is equal to nothing but a linear combination of x1i, and x2i is equal to lambda x1i. In other words, lambda is equal to a non-zero constant. Okay, before I leave this slide, I just want to make sure that we are all aware that all the y's and the x's here are not just y's and x's, but all of these are deviations from the mean. Okay, so for example, if I write the sum of yi xi, just make sure that you understand that yi is a deviation from the mean. So in other words, when I write as yi, then it's basically, put it in your mind that it's yi minus y bar. Okay, so it's a deviation from the mean. And when you see it as xi, then just understand that what we have here is just, we're trying to make our life easy by making the formula looks kind of simpler, but if we put all the deviations from the mean, it will look like more of a kind of an expanded version. So just make sure that you understand that even xi is simply xi from x bar. Okay, so if it is x1i, then it's x1i from x1 bar. Okay, if this is for x1, for example. So all of these different parts of the beta equation, all of these are deviations from the mean. This thing is also deviation from the mean, right? So it's xi minus x bar squared. Okay, and this one is the same thing. So this one is the sum of yi minus y bar in a bracket, and then you open another bracket, x1i minus x1 bar. Okay, so what we have here is just all the y's and x's. Just put in your mind that all of these are deviations from the mean. What about if I have a case that is not perfect? Okay, so before I leave this, just make sure that I'm sorry, let me just erase this. So I was just writing something. Okay, for some reason my pen is not working as nice as yesterday. I need to replace it, so I'll try my best to write the equations. Okay, so let me clean this thing. Okay, so just make sure that if I have a perfect multicollinearity in a model that is 1 yi equals to let's say beta hat 1 x1 I plus beta hat 2 x x2I, as I'm telling you, my pen is not working as nice as yesterday, so this is x2I plus ui. Okay, so if I have a perfectly collinear, in which a case that, as we said, x2I is equal to lambda x1I. In this situation, right, there is no way I can estimate, for example, the effect of x1 on y holding x2I constant, right? So anytime x1 changes, so does x2I by the factor lambda. So you have to make sure that the presence of perfect collinearity in the model would make the estimation of the betas, where the betas is the change in y because of the change on whatever xi, for example, could be like x1 or x2. The estimation of the parameters will not be accurate, right? Because each of these parameters kind of implicitly has the impact of the other factor. And we have seen that anytime we can see x2I, we can just replace it with lambda x1I, and then by the end this would make the numerator and the denominator equal to 0, so I won't be able to estimate beta. Okay, so let me show you another example. So a case in which I have x2I is not perfectly collinear with x1I. So in this situation, you can write it this way. What about if x2I, I'm sorry, I'm going to buy another pen. X2I is equal to lambda x1I plus a certain disturbance variable, let's say vi. Okay, so in this situation I cannot say I have perfect collinearity. If I stop here, I'm going to say perfect collinearity, but if I add this disturbance term, the presence of this term or the presence of this error term will kind of dilutes the perfect collinearity between x1I and x2I. Okay, so in other words, I cannot just replace x2I everywhere in the equation with lambda x1I, because I still have another term here, which is the error term of this equation. And of course, it makes sense as this error term decreases, the connection between these two increases, would make the multicollinearity problem worse. Okay, I want you also to think about this model as if you can write it also this way, but I'm just making my life easy by not thinking about an intercept. But x2I can also be equal to lambda 0 plus lambda 1 x1I plus vi. So I can have an error term and I can have an intercept, right? But I'm just thinking, okay, let me just remove the intercept for simplicity, because the main message is coming from the error term. The presence of the error term dilutes this perfect collinearity or multicollinearity between x1I and x2I.